Red River Valley, Minnesota territory. Winter of 1876. While his neighbors stacked stone upward, building their fireplaces tall and proud, according to every known principle of American construction, one Norwegian immigrant was digging downward. They called him mad. They said his family would choke on smoke within a week. Expert masons shook their heads. Experienced builders warned anyone who'd listened that this fool was violating the most basic law of chimney draft. But when the coldest winter in recorded memory descended on the valley, something impossible happened. While conventional cabins filled with smoke and struggled to maintain heat, his sunken hearth burned cleaner, hotter, and on half the wood. What did this Norwegian homesteader understand about fire and physics that American builders had missed? If you want to discover forgotten survival engineering that actually worked, hit that like button, subscribe, and drop a comment telling us what traditional building technique you'd want to see tested. Red River Valley, Minnesota Territory, September 1876. Olav Thorsen arrived in the Minnesota Territory with nothing but a wagon, his wife Ingrid, 2 children, and a memory that wouldn't let him go. Back in Telemark, Norway, every farmhouse he'd known had a hearth that sat below floor level. Not above, not level, below. His neighbors along the Red River thought he'd lost his mind. "You're building it wrong," Jacob Mueller told him, watching Olav dig a pit 3 feet deep where his fireplace should rise. Mueller had built 7 cabins in Dakota and Minnesota. He knew chimneys. Smoke rises, Norwegian. You put the fire down in a hole, you'll suffocate your family. Olav didn't argue. He just kept digging. The hole measured 4 feet wide, 3 feet deep, lined with field stone he'd hauled from the riverbed. While other homesteaders were raising fireplaces upward, stacking stone to waist height before transitioning to the chimney, Olav was creating what looked like a stone-lined grave in the center of his cabin floor. "It's a hearth," he said simply, his English still rough. "Ildsted, like home." Thomas Bradley, the settlement's recognized mason, rode out specifically to stop what he called this dangerous experiment. Bradley had apprenticed in Pennsylvania. He'd built fireplaces for wealthy families in St. Paul. He understood draft, draw, and the fundamental principle that heat rises. "Mr. Thorsen," Bradley explained with the patience of a man addressing a child, "the firebox must be elevated to create proper draft. Your chimney will pull air downward. Smoke will pool in that pit. You're creating a death trap." Ingrid Thorsen stood in the doorway, hands twisted in her apron. She'd heard the warnings. Every woman in the settlement had warned her. They spoke of families found dead, asphyxiated by smoke in poorly designed cabins. But Olav had watched his grandfather tend a sunken hearth for 40 winters in Norway. He'd learned to build fire from a man who never once filled a house with smoke. "I know smoke," Olav said quietly. "I build it right." By October, his cabin stood complete. The sunken hearth dominated the central room, its stone rim rising just 6 inches above the floor planks. The chimney, built from clay-daubed fieldstone, rose straight and true through the roof peak. Around the hearth perimeter, Olav had built a low stone bench, 18 inches wide, that encircled 3 sides of the pit. The settlement waited for the inevitable disaster. Sarah Mueller, Jacob's wife, brought Ingrid a basket of dried herbs and a warning. "When the smoke gets bad, burn these. Juniper helps. And keep a wet cloth over the children's faces at night." Ingrid accepted the herbs with a thin smile. She'd already split kindling the Norwegian way, exactly as Olav had shown her. Thin, dry, arranged in a specific pattern she didn't yet understand, but trusted completely. On October 15th, 1876, as the first hard frost settled over the valley, Olav Thorsen lit his first fire in the sunken hearth. The settlement's men found reasons to walk past his cabin that evening. They expected to see smoke billowing from the door, to hear coughing, to witness the predictable failure of old-world ignorance confronting new-world reality. Instead, they saw a chimney drawing cleanly, a thin gray stream rising straight into the darkening sky. Through the window, Olav sat calmly on the stone bench surrounding his fire pit, carving a butter mold while his children played at his feet. Not a wisp of smoke inside the cabin. Jacob Mueller stood in the cold, staring at that window, trying to understand what he was seeing. Must be a fluke, Thomas Bradley said. Wait until he really loads it with wood. Wait until winter truly hits. That's when physics will catch up with foolishness. But something in Bradley's voice had changed. The absolute certainty had cracked, just slightly, because what they were witnessing shouldn't be possible. And winter was coming. The technical design of Olav Torsson's Sunken Hearth violated every principle Thomas Bradley had learned in 15 years of masonry. Yet it worked. That impossibility gnawed at Bradley through October and into November. Finally, professional pride overcame prejudice. He needed to understand. On November 3rd, 1876, Bradley arrived at the Torsson cabin with a measuring tape, a notebook, and a willingness to admit he might be wrong. What he documented changed his understanding of fire. The hearth pit measured 42 inches in diameter and 36 inches deep. Olav had lined it entirely with river fieldstone, fitted tight enough that mortar barely showed. But the crucial detail wasn't the pit itself. It was the bench. The stone bench surrounding the hearth extended 18 inches into each wall, creating massive thermal mass exactly at sitting height. Bradley calculated roughly 4,000 pounds of stone encircling that fire pit, all of it positioned to absorb and radiate heat at the level where humans actually lived. Conventional fireplaces, Bradley muttered, sketching in his notebook, we build them up. Heat rises to the ceiling. Wasted. Olav nodded. Heat stays low, where people are. The chimney design baffled Bradley initially. It rose from the back edge of the pit, transitioning from an 18-inch square base to a standard 8-inch flue about 3 feet up. That transition created natural restriction that seemed wrong. Every instinct said it would choke the draft. Should smoke, Bradley said, pointing at the restriction. Should, Olav agreed. But watch. He built up the fire, adding split oak until flames filled half the pit. Bradley watched, notebook ready to record the failure. Instead, he watched the smoke column tighten, accelerate through the restriction, and blast upward with such force it created an audible draw. The physics defied his training. Then, slowly, understanding dawned. A conventional fireplace sat at floor level or slightly elevated. Cold air entered the firebox at the same level where heat tried to escape. They fought each other. Draft became a constant battle between incoming cold and rising heat. But Olav's sunken design separated those flows vertically. Cold air flowed down into the pit from all sides, feeding the fire from below. Hot gases rose from the center, already concentrated and accelerating. No interference, no turbulence. The fire breathed like a lung, perfectly efficient. The pit creates a combustion chamber, Bradley said, understanding flooding through him. Like a forge. Ja, Olav said. Like forge. The secondary burn fascinated Bradley most. In a conventional fireplace, smoke was wasted fuel escaping up the chimney. But in Olav's design, the restricted chimney base held heat down long enough for secondary combustion. Smoke gases ignited before escaping, releasing their energy as heat instead of creosote. Bradley measured the temperature differential. Using a mercury thermometer, he recorded 68 degrees Fahrenheit at head height in the Torsson cabin, while outdoor temperature held at 22 degrees. His own cabin, with a conventional raised hearth burning similar wood, maintained 54 degrees at best, 14 degrees warmer, on what he estimated was 60% of the wood consumption. The stone bench explained the rest. For 1,000 pounds of fieldstone absorbed heat for hours while the fire burned hot, then radiated it back for hours after the fire died. Olav showed him the pattern. Burn hot and fast for 3 hours in the evening, bank the coals overnight, wake to a cabin still comfortably warm from yesterday's heat stored in stone. In Norway, Olav explained, we burn less, heat more. Bradley spent 4 hours documenting measurements. Stone thickness, 8 to 12 inches throughout. Pit depth to chimney base, precisely 36 inches, creating what he now understood was optimal combustion chamber height. The bench width, 18 inches, extending the thermal mass far enough to matter, but not so far it lost heat to exterior walls. Every dimension served a purpose. Thomas Bradley left the Torsson cabin, that afternoon, carrying 15 years of professional certainty in one hand and a notebook full of evidence in the other. The evidence was winning, but he wasn't ready to admit it publicly. Not yet. He told himself he needed more data, a longer observation period, winter's real test. The truth was simpler and harder to face. He'd been wrong, and a Norwegian immigrant with broken English had been right. About physics, about fire, about the fundamental design of the tool humans had used for 10,000 years to survive winter. His pride needed time to catch up with his data. Jacob Mueller asked him that evening what he'd learned. "Nothing conclusive," Bradley said, the lie tasting like ash. "We'll see what winter brings." But in his notebook, in handwriting he showed no one, he'd written, "Design is sound. Possibly superior. Requires further study, but preliminary evidence suggests significant efficiency gains. American conventional design may be fundamentally flawed." The next day, he returned to his own cabin and stared at his fireplace with new eyes. He'd built it proud, tall, efficient by every standard he'd been taught. And it was wrong. The Sunken Hearth wasn't Norwegian innovation. It was Norwegian memory. Olav Thorsen carried knowledge that stretched back through centuries of Scandinavian winters, but the principle was older still. Humans had discovered it independently across every cold climate on Earth. The Japanese had their Aurori, the Koreans their Andal, the Russians their Podpeki. Different names for the same understanding. Fire works better when you work with physics instead of against it. What Thomas Bradley called common sense was actually recent invention, barely a century old. American fireplace design evolved from English Georgian fashion, optimized for cold and mild climates. Built tall because tall looked impressive in wealthy homes. Function followed form. Efficiency was never the goal. The physics Olav understood was simpler and older. Heat moves three ways: conduction, convection, and radiation. A conventional fireplace tries to heat a room primarily through convection, sending hot air upward where it pools uselessly against the ceiling. Perhaps 30% of the fire's energy actually warms the living space. The rest escapes up the chimney or radiates into masonry that sits too high to warm anything humans touch. But a sunken hearth reverses the equation. Radiation becomes primary. For 1,000 pounds of stone at bench height absorbs infrared energy directly from the fire, then radiates it outward at exactly the level where people sit, sleep, and work. The stone acts as a thermal battery, charging while fire burns, discharging for hours afterward. Olav's family lived inside the heating zone, not below it. Convection still happens, but controlled. Hot air rises from the pit through the living space, warming on the way up instead of bypassing it entirely. The sunken design creates a convection current that pulls cold air down into the pit from floor level, heats it intensely in the combustion chamber, then sends it up through the room as a warm column. The entire cabin becomes part of the heating system. Conduction through the stone bench creates warm seating. In a Minnesota winter, the difference between sitting on wood at 50 degrees and sitting on stone at 70 degrees is the difference between discomfort and comfort, between burning extra wood to warm air or burning less wood to warm mass. The secondary combustion Bradley observed wasn't accidental. The restricted chimney base created a high-temperature zone where smoke gases had time and heat to ignite. Modern forced air furnaces burn at around 70 to 80% efficiency. Olav's Sunken Hearth, built with river rocks and clay, was achieving something close to that through pure geometric design. Less creosote meant cleaner chimneys. Cleaner chimneys meant fewer fires. Fewer fires meant family survived. But the American builders couldn't see it. They learned that chimneys must be tall, that fireboxes must be elevated, that draft required height and more height. They'd learned wrong, but they'd learned it from men they respected, from books published in Philadelphia and Boston, from a building tradition that worked adequately enough that no one questioned it. Adequate beats innovation until crisis proves otherwise. The cultural blindness ran deeper than Bradley realized. When he looked at Olav's hearth, he saw primitive backwardness, a stubborn immigrant clinging to old country ways. He couldn't see what Ingrid Thorsen saw: her grandmother's hearth, her mother's hearth, 40 generations of Norwegian women who'd cooked and warmed and raised children beside sunken fires that never failed. Women knew. They tended fire daily. They understood intimately which designs worked and which wasted wood their men had labor to cut. But in 1876 Minnesota, women's knowledge about domestic engineering was dismissed as superstition beneath the consideration of professional men. So Bradley documented measurements while Ingrid could have explained in 5 minutes what took him 4 hours to discover. The settlement's resistance wasn't about physics. It was about pride and the pain of being wrong. American frontier culture valued innovation, but only when Americans did the innovating. Let a Norwegian immigrant dig a hole and call it progress? That threatened the natural order. The old world was supposed to be backward. The new world was supposed to be enlightened. A Sunken Hearth reversed that narrative, and narratives die harder than facts. What Olav knew and Bradley slowly discovered was that traditional knowledge isn't primitive. It's laboratory tested across centuries of survival. Every inefficient design killed its builders through wasted fuel or chimney fires. Every efficient design propagated through imitation. Natural selection worked on hearths as ruthlessly as on organisms. The Sunken Hearth survived because it worked. It worked because it aligned with physics. Physics didn't care about national pride or professional credentials. Winter was about to prove that conclusively. January 12, 1877. The temperature fell to 18 degrees below 0 Fahrenheit, 49 below the freezing point. Cold enough to kill. The Red River Valley had endured hard winters before, but nothing in living memory matched that January. The cold arrived suddenly, a high-pressure system that settled over Minnesota territory and refused to move. For 6 days, temperatures never rose above 0. At night, they plunged into ranges where exposed skin froze in minutes, and poorly heated cabins became death traps. Thomas Bradley woke on January 13th to find ice on the inside of his windows and his water bucket frozen solid despite sitting 3 feet from his fireplace. He fed his fire constantly, burning through what he'd rationed for 2 months. By mid-afternoon, his cabin held at 47 degrees. Livable, but barely. His children huddled under blankets. His wife wrapped heated stones in cloth to keep their feet from freezing. They were burning 36 pounds of split oak every 24 hours. At that rate, their supply would last 3 weeks. If the cold held longer, they'd face choices no family should face. Before we see what happened next, hit that like button and subscribe. The physics of survival gets even more interesting. Drop a comment with your guess. How much warmer could a sunken hearth actually be in this killing cold? Jacob Mueller's situation was worse. His fireplace smoked whenever he loaded it heavily enough to fight the cold. The smoke forced him to choose between warmth and breathable air. He chose air, kept the fire smaller, and watched his family shiver at 52 degrees while burning through his wood supply even faster than Bradley. Sarah Mueller tried everything. She hung blankets to trap heat near the fireplace. She heated stones and bricks, rotating them from fire to beds. She burned the juniper she'd given Ingrid Thorsen, hoping the aromatic smoke might somehow warm better than oak. Nothing worked. Physics didn't negotiate. Other families fared no better. The Peterson cabin held at 49 degrees. The O'Malley family crowded into one room, abandoning the rest of their house to the cold. The Swenson family seriously discussed whether they should abandon their claim and retreat to St. Paul until spring. And then, on the 3rd day of the brutal cold, Jacob Mueller walked past the Thorsen cabin. What he saw made no sense. No smoke poured from the door. The chimney drew cleanly, a thin gray column in the still air. Through the window, Jacob saw Ingrid Thorsen working at her table in her everyday dress, not bundled in layers. The children played on the floor. Olaf sat on the stone bench around his hearth, relaxed, reading by firelight. Mueller approached the door. Before he could knock, Olaf opened it. The wave of heat that rolled out felt like summer. "Come," Olaf said. "Too cold to stand outside." Mueller stepped into warmth, so complete, so enveloping, it felt impossible. The cabin was warm everywhere, not just near the fire. Everywhere. The walls radiated gentle heat. The floor felt comfortable through his boots. The air temperature at head height felt like a mild spring day. He stared at the sunken hearth. A modest fire burned in the pit, smaller than the roaring blaze Mueller maintained in his own fireplace. Yet the heat was incomparable. "Ow!" Mueller managed. Olaf gestured to the stone bench. "Sit. Feel." Mueller sat. The stone beneath him was warm, almost hot, radiating heat upward into his body. After 3 days of huddling near an inadequate fire, the sensation was overwhelming. He felt his muscles unclenching, warmth spreading through him like he was thawing from the inside out. "The stone," Olaf explained, "it drinks heat all day, gives it back all night. Fire burns 3 hours, stone warms 12 hours. Mueller looked around the cabin again, understanding dawning. The massive stone bench wasn't decoration. It was the heating system. For 1,000 pounds of thermal mass, charged by an efficient fire, radiating stored energy long after the flames died. "Temperature?" Mueller asked. Olaf checked the mercury thermometer hanging on the far wall. 71, he said. This morning, before fire, was 63. 71 degrees. While Mueller's cabin struggled to maintain 47. A 24-degree difference. In killing cold, on what Olaf casually mentioned, was 3 hours of fire, morning and evening. 6 hours of burning versus Mueller's constant feeding. 71 degrees versus 47. The numbers were devastating. "How much would?" Mueller asked, though he dreaded the answer. Olaf shrugged. "Today, maybe 18 pounds. 2 days ago, 20. Mueller was burning 36 pounds a day to achieve half the warmth. Olaf was burning half the wood to achieve twice the comfort. The efficiency difference wasn't marginal. It was catastrophic. It was the difference between surviving winter comfortably and barely surviving at all. Mueller sat on that warm stone bench, feeling heat soak into his frozen body, and faced a truth harder than the cold outside. Everything he believed about heating a cabin was wrong. The experts were wrong. The American way was wrong. The Norwegian way, the way they'd all mocked, the way they'd warned would kill its builders, was right. And they called Olav a fool. "I need to tell Bradley," Mueller said quietly. Ja Olav agreed. "You tell him. Tell everyone." Too cold for pride. That evening, 7 men stood crowded in the Torsen cabin, feeling the impossible warmth, staring at the sunken hearth like it was a miracle instead of applied physics. 7 men who'd warned Olav against digging that pit. 7 men whose families were suffering while Olav's thrived. Thomas Bradley stood silent, his notebook useless. All his measurements, all his professional knowledge, all his certainty had led him exactly wrong. The data didn't lie. His training had. The temperature outside was 16 below zero. Inside, the Torsen cabin, surrounded by 4,000 pounds of heated stone, the temperature held steady at 71 degrees Fahrenheit. The math was simple. The implications were devastating. Winter had declared its verdict. The measurements began at dawn on January 14, 1877. Thomas Bradley arrived at the Torsen cabin with 3 mercury thermometers, a notebook, and the kind of methodical determination that comes from having your entire professional foundation cracked open. He needed numbers, not impressions, not feelings. Numbers that could prove or disprove what 7 witnesses had experienced the night before. Bradley established his testing protocol with scientific rigor. He would measure temperature at 3 heights, floor level, sitting height, and head height, in both the Torsen cabin and his own. He would record wood consumption by weight. He would document fire duration, smoke clarity, and heat retention after the fire died. The outdoor temperature held at 14 below zero. Perfect testing conditions. Brutal, but perfect. At the Torsen cabin, Olav built his morning fire at precisely 6 a.m. Bradley recorded the process. Olav used 18 pounds of split oak, arranged in a specific pattern Bradley sketched carefully. The wood was split thin, no piece thicker than 3 inches. Olav built the fire in layers, kindling at the pit bottom, progressively larger splits arranged in a loose crosshatch pattern that allowed air flow from below. The fire caught immediately. No smoke in the cabin. The draw was so strong Bradley could feel air flowing past his ankles toward the pit. He took his first temperature readings at 6:30 a.m., 30 minutes after ignition. Floor level, 58 degrees Fahrenheit sitting height. At the stone bench, 64 degrees head height. 61 degrees, the temperature profile made no sense by conventional understanding. Sitting height was warmest. In a normal cabin, heat stratified upward, leaving the floor cold and the ceiling hot. But here, the heated stone bench created a warm zone exactly where humans lived. At 7 a.m., 1 hour after lighting, floor level, 62 degrees sitting height, 69 degrees head height, 66 degrees. The stone was absorbing energy, warming steadily, beginning to radiate. The cabin temperature climbed not from convection alone, but from thermal mass coming online. At 9 a.m., 3 hours after lighting, Olav let the fire die to coals and covered them with ash. Bradley protested. "You're stopping? It's 14 below outside. The stone will work now," Olav said simply. Bradley continued measuring. This was the crucial test. How long could thermal mass maintain heat without active fire? 9:30 a.m., 30 minutes after fire died. Floor level, 64 degrees sitting height, 71 degrees head height, 67 degrees. The cabin was getting warmer with no fire burning. 10 a.m., 1 hour after fire died. Floor level, 65 degrees sitting height, 72 degrees head height, 68 degrees still warming. The stone bench was discharging stored energy faster than the cabin lost heat to the outside. Bradley placed his hand on the stone. It was hot enough to be uncomfortable, easily above 130 degrees Fahrenheit at the surface. Noon, 3 hours after fire died. Floor level, 63 degrees sitting height, 70 degrees head height, 66 degrees. The temperature had peaked and was declining, but slowly. So slowly. 2 p.m., 5 hours after fire died. Floor level, 59 degrees sitting height, 65 degrees head height, 62 degrees, still above 60 degrees everywhere. 5 hours after the fire went out. With outdoor temperature at 12 below zero. Bradley did the math. Olav burned 3 hours in the morning, 3 hours in the evening. 6 hours total. The stone provided comfortable heat for roughly 12 hours total. The other 6 hours, overnight, temperature dropped to what Olav had shown him. Low 60s by morning, which was perfectly tolerable under blankets. Wood consumption for the entire day, 36 pounds total, split between morning and evening fires. Bradley returned to his own cabin to establish baseline comparison. His conventional fireplace required constant feeding to maintain temperature. He measured his own consumption. 42 pounds of wood per day, burned continuously with only brief banking overnight. His cabin temperatures at noon, with fire actively burning. Floor level, 43 degrees sitting height, 51 degrees head height, 56 degrees, 14 degrees colder at sitting height than the Torsen cabin 5 hours after its fire had died, while burning more wood continuously. The efficiency difference was staggering. Olav's Sunken Hearth, 72 degrees peak, 60 degrees minimum, 36 pounds wood per day, 6 hours burning. Bradley's raised hearth, 56 degrees peak, 40 degrees minimum, 42 pounds wood per day, 18 hours burning. The Torsen family lived in comfort. Bradley's family endured survival conditions. The engineering difference wasn't subtle. It was life-changing. But Bradley needed one more test. He needed to understand smoke production and chimney performance. On January 15th, he climbed on both roofs at noon to observe the chimneys under load. His own chimney poured thick gray smoke, heavy with unburned particles. Creosote would build rapidly. He needed to clean it frequently or risk fire. The Torsen chimney emitted a thin, nearly invisible heat shimmer. Bradley could barely see the exhaust. The secondary combustion was burning smoke gases before they could escape. Less smoke meant less creosote, meant safer operation, meant the design was superior in every measurable way. Jacob Mueller joined him on the Torsen roof. They stood in 14 below cold, staring at that nearly invisible exhaust, and Mueller spoke the truth both men had been avoiding. "We built wrong," Mueller said. All of us. For years. Bradley nodded slowly. Not wrong exactly. Adequately. But adequate isn't optimal. And Olav built optimal. From memory, Mueller added. He wasn't inventing. He was remembering. That distinction mattered. This wasn't frontier innovation. This was old-world knowledge that American builders had dismissed as primitive. The arrogance of that dismissal was now undeniable. Bradley spent the evening filling his notebook with calculations. Heat retention rates, thermal mass capacity, combustion efficiency, draft velocity. Every measurement confirmed what his pride had resisted. The Sunken Hearth was fundamentally superior to conventional American fireplace design. The next morning, January 16th, 7 families gathered at the Torsen cabin. Not to mock, not to warn, to learn. Olav Torsen, the Norwegian immigrant they'd called a fool, spent 3 hours explaining in broken English what his grandfather had taught him in perfect Norwegian. How to dig the pit, how to line it with stone, how to build the bench, how to proportion the chimney, how to split wood for maximum efficiency, how to tend the fire for thermal mass, charging rather than continuous burning. The men took notes. The women asked questions Bradley had never thought to ask, practical questions about cooking temperatures and ash management and child safety around a pit fire. By sunset, plans were drawn. Measurements were recorded. Consensus had formed. The Sunken Hearth would spread. Spring 1877 brought change to the Red River Valley, but the real transformation had happened during winter's brutal test. Thomas Bradley returned to masonry that April, carrying knowledge that made him both humbler and better at his craft. The first new Sunken Hearth broke ground at the Mueller cabin in late April. Jacob Mueller insisted that Bradley oversee the construction, not because Bradley knew the design better than Olav. He didn't, but because Mueller wanted American hands to build American acceptance of Norwegian wisdom. Bradley and Olav worked together. The collaboration was awkward initially. Bradley had dismissed Olav's knowledge for months. Apologies had been made, but apologies don't erase memory. They worked through the discomfort toward something better. Mutual respect built on shared purpose. The Mueller hearth followed Olav's specifications exactly. 42 inches wide, 36 inches deep, stone bench extending 18 inches into the walls. Bradley brought his mason's precision to the stonework, fitting river rocks so tightly that thermal mass approached solid stone performance. Olav contributed the proportions and geometric understanding that made precision matter. They completed it in 8 days. Jacob Mueller lit his first fire on May 3, 1877, in weather too warm to truly test the design. But he felt the stone bench warm beneath him, felt heat radiate outward in a pattern completely different from his old fireplace. And new winter would prove what spring merely promised. By June, 3 more families had begun excavation. The Petersons, the O'Malleys, and the Swensons, all families who'd struggled through January's cold. They'd endured 40-degree cabins while the Torsen family had thrived in 70-degree comfort. Pride had its limits. Frozen children were more persuasive than frozen pride. If you're learning something valuable about forgotten engineering, show your support with a like and subscribe. And comment below, what other old-world building techniques should have survived into modern times? Sarah Mueller became an unexpected advocate. Women's networks moved information faster than men's, and women cared more about practical results than theoretical principles. Sarah had visited Ingrid during that January cold, had felt the warm stone bench, had seen her children comfortable instead of huddled. She told other women. The women told their husbands. By autumn 1877, 9 families in the Red River Valley had built or were building sunken hearths. Olav's design spread with modifications. The Petersons added a small oven chamber in their stone bench, using trapped heat for baking. The O'Malleys oriented their hearth east-west instead of north-south, claiming better morning light for cooking. Olav approved both changes. The principle mattered more than rigid adherence. Thomas Bradley documented every variant. His notebook from 1877 to 1878 became a manual of vernacular engineering, filled with sketches, measurements, and performance notes. He tested thermal mass variations, river rock versus quarried limestone versus mixed stone. He measured retention rates with different bench widths. He experimented with chimney restrictions, finding the optimal balance between draw and secondary combustion. The data accumulated into understanding. Sunken hearths weren't a single solution, but a design family. The core principles: thermal mass at living height, combustion pit for efficiency, strategic chimney design, remain constant. The details adapted to available materials, family size, and cooking requirements. By late 1878, 17 cabins within 50 miles incorporated Olav's core design. Some were pure Norwegian style. Others were hybrid adaptations, combining sunken hearth principles with American construction preferences. All performed better than conventional fireplaces. The efficiency gains were consistent across implementations. 30 to 40% reduction in wood consumption, 15 to 25-degree higher interior temperatures, 12 to 16 hours of heat retention, from 3 to 4 hours of burning, dramatically reduced smoke and creosote production. The families who'd adopted the design weathered the winter of 1877 to 1878 in comfort that seemed almost luxurious compared to previous years. Wood supplies stretched further. Children played on warm floors instead of huddling near inadequate fires. The stone benches became social centers, places where families gathered not just for heat, but for the comfort heat enabled. Economic impacts spread beyond individual comfort. Families burning less wood spent less time cutting wood. Men could dedicate more hours to other work. Spring planting started earlier because winter hadn't exhausted everyone. The efficiency gains compounded into broader prosperity. The settlement's recognition of Olav Thorsen shifted fundamentally. In September 1876, he'd been a fool digging a dangerous hole. By September 1878, he was consulted on every new cabin construction. His broken English hadn't improved much, but it didn't matter. People listened differently now. They heard knowledge where they'd once heard ignorance. Jacob Mueller summed it up one evening, sitting on his own warm stone bench in December 1878. We thought we were teaching him the American way. Turn out he was teaching us the way that works. The spread continued. By 1880, the sunken hearth design had reached settlements beyond the Red River Valley. Scandinavian immigrants carried it south into Iowa and west into Dakota Territory. American families carried it east into Wisconsin. The design moved through networks of survival knowledge, passed from neighbor to neighbor with the urgency of information that kept children alive. Thomas Bradley built his final conventional raised fireplace in October 1877. After that, every hearth he built incorporated sunken design principles. He charged less for them initially. They used less stone, less labor, just better geometry. But he charged more eventually once people understood what they were buying. Not a fireplace, but a heating system that worked with physics instead of fighting it. He never advertised himself as a Norwegian-style mason. Pride remained. But in his personal notebook, in the design drawings he considered his real legacy, he titled the section, Thorsen Principles, Thermal Mass Application for Frontier Heating Systems. It was as close to apology and tribute as a 19th-century American mason could manage. The wisdom had spread, not through academic publication or official endorsement, but through the oldest form of validation. It worked, people saw it work, people copied it. Winter by winter, the knowledge accumulated. Cabin by cabin, families survived better. That was how engineering actually progressed. Not through revolution, but through cold families observing warm families and asking the right questions. The story of Olav Thorsen's Sunken Hearth isn't really about one Norwegian immigrant in one Minnesota valley. It's about a pattern that repeated across the frontier wherever traditional knowledge collided with American certainty. The old world knew things the new world had forgotten, or more accurately, had never learned because they never needed to. European peasants in harsh climates had spent centuries optimizing heat efficiency because wasted heat meant death. American builders in the 1870s were maybe 3 generations removed from those pressures. They developed adequate solutions for milder climates and smaller temperature extremes. Adequate worked until it didn't. The winter of 1877 was one of those moments when adequate failed and optimal survived. What Bradley's measurements proved was that traditional knowledge wasn't primitive. It was laboratory tested across centuries of survival. Every inefficient hearth killed its builders through hypothermia or wasted labor. Every efficient design propagated through desperate imitation. Natural selection worked on engineering as ruthlessly as biology. The sunken hearth survived that selection because it aligned with fundamental physics. Thermal mass at living height. Secondary combustion. Separated air flows. Radiant heat where humans actually lived. These weren't superstitions or old country stubbornness. They were applied thermodynamics discovered through trial and error across generations. The broader lesson extended beyond hearths. The frontier was full of dismissed wisdom. Native American fire management that prevented catastrophic burns. Hispanic adobe construction that regulated temperature without fuel. Chinese mining techniques that prevented collapses. Immigrant farming practices that preserved soil. American builders often ignored these methods. Not because they didn't work, but because acknowledging they worked meant admitting that the new world had something to learn from people they consider backward. Pride is expensive. It cost families comfort through that January cold. It cost communities what they couldn't spare. It cost children warmth their bodies needed for growth. Pride was expensive, and the families who abandoned it survived better. Olav Thorsen never claimed credit for inventing anything. He just built his grandfather's hearth and let winter prove whether memory was wiser than expertise. When winter rendered its verdict, he taught anyone who asked. No resentment for the mockery. No bitterness about the warnings that his family would suffocate. Just quiet willingness to share knowledge that worked. That generosity mattered as much as the engineering. Traditional knowledge survives through teaching, through elders patiently showing younger hand how to split wood, how to proportion stone, how to read fire's behavior in a pit. Olav could have hoarded his knowledge, let his neighbors freeze while he stayed warm, claimed vindication through their suffering. Instead, he taught them, because survival knowledge is communal or it dies. A warm cabin surrounded by frozen neighbors doesn't survive. The community survives together or fails together. The sunken hearth spread through the Red River Valley, but the principles spread further. Other traditional techniques gained attention. Norwegian roof construction, Swedish log joinery, Finnish sauna design. Once people accepted that old-world knowledge might be optimized rather than outdated, they started looking for other dismissed wisdom. Thomas Bradley's notebooks from 1878 to 1885 document that expansion. He tested traditional techniques systematically, measuring performance, comparing results, determining which methods actually worked better and which were genuinely obsolete. Not all traditional knowledge was superior. Some was superstition. Some was optimized for conditions that didn't exist in Minnesota. But much of it was better. And Bradley, to his credit, admitted that. His late career work combined American precision with European principles. He became a bridge between worlds, translating traditional knowledge into measured data that other American builders could accept. He died in 1891, 15 years after watching Olav Thorsen dig that first pit. His obituary mentioned him as a master mason who helped introduce European heating efficiency to frontier construction. It didn't mention that he'd fought that introduction for months or that he'd called Olav a fool. History polished away his resistance, leaving only his eventual contribution. That's probably fair. People deserve credit for changing their minds when evidence demands it. Pride that yields to data is still valuable, even if humility from the start would have been better. Olav Thorsen lived until 1903. By then, dozens of families in 3 states heated their homes with sunken hearths built on his grandfather's principles. Children who'd grown up warm on stone benches built their own hearths the same way. The knowledge had propagated, become regional tradition, would eventually fade as central heating and furnaces replaced fireplace heating entirely. But for 30 years, in a specific time and place, Olav's memory of his grandfather's hearth kept families warm. That's not a small legacy. That's lives saved through applied physics and cultural humility. The final lesson is simple and hard. Dismissing traditional knowledge as primitive often reveals not their ignorance, but ours. Every culture that survived harsh conditions developed sophisticated solutions. Those solutions might look strange to us. They might violate our assumptions about proper design. But if they worked for centuries, if they kept families alive through winters that killed the unprepared, then maybe, just maybe, we should ask why they work before explaining why they can't. Olav Thorsen asked that question by building his grandfather's hearth and letting results speak louder than experts. The result was a cabin that stayed 72 degrees while neighbors froze at 47. The result was families who survived winter comfortably instead of desperately. The result was wisdom proving itself through the oldest test humanity knows. Does it work when survival demands it? That January in 1877, the Sunken Hearth passed that test decisively. If this story of forgotten engineering wisdom resonated with you, hit that like button one more time and subscribe for more deep dives into traditional knowledge that actually worked. Drop a comment sharing any old world technique your family still uses or wishes they preserved. The past has lessons we're still learning. Traditional knowledge isn't nostalgia. It's survival data tested across generations, optimized through crisis, proven by the simple fact that the people who used it lived long enough to teach it. Sometimes the old world knew better. Sometimes the fool digging a hole understood physics the experts missed. Sometimes memory is wiser than innovation. The stone bench stays warm long after the fire dies. That's not magic. That's thermal mass and radiant heat and geometric design optimized across centuries. That's traditional knowledge working exactly as it always did, quietly, efficiently, keeping families warm while the skeptics freeze.